Ryan.
Recording.
Okay. Trying to make it fun. All right. Today we want to start talking about states of matter. All right. So what do we mean states of matter? Give me some states of matter. Solid, liquid, gas, right? Plasma. There's
The other two that Ski was talking about.
What's the other one?
I forget them every time.
there's like
There's
a
some really long names.
there's like a gelatin type. It's got a name. I don't know, like toothpaste. All right. I forget what it's called. That kind of matter. But we're just going to deal with the simple three basic: solid, liquid, gas. Right. But there's a lot more. But for our purposes, that's what we're going to deal with today. So solid. We're going to picture solid as an array of atoms connected by bonds, which I'm going to draw as springs. Right, this is getting tiresome. Right, connected by springs in an array. That's going to be our picture of a solid. Make sense, everybody? Okay, liquid. Oh, let's go to gas. Gas the other end. So we have solid, we have gas. We already saw a model of a gas the other day when we did ideal gas law. What was our model of a gas?
Like fast moving molecules.
Yeah, with no connections, right? They're free to move. Right? So the question is liquid. Now, there's probably different models of liquids. I'm just going to use one that I like. Maybe it's not the best, but it helps in what we're going to deal with in this topic of specific heat and latent heat. That's what we're going to be talking about. So I'm going to picture a liquid as molecules connected in pairs. And of course, that's not really what it is, but
Just springs.
those little springs, yeah. The springs represent intermolecular bonds. If you really want to think about it, there's some weak bonds in between the other ones. There's like hydrogen bonding, so there's weak bonds in there, but we're going to ignore them. This is just a mental picture so we can understand what's going on, right? It's not the accurate, absolute definition. This will help us picture what's going on. So, we're going to heat this stuff and see what happens, okay? So let's start with a solid. So I'm going to erase the liquid and gas. Start with our solid, see what happens. I have a little simulator for that, so we can see. It's in the other course. I gotta copy these simulators into your course. I'll try to do that this weekend. I have all these simulators in the other course. All right. Okay, so here we have two objects. Notice these have little white lines. These have big yellow lines. There's this quantity called specific heat we're going to talk about. They have different specific heats. Okay. The specific heat is the property of the material. I guess I can give you the definition. Of course, how do we define things in physics? With formulas, right? So specific heat is the symbol C, and it's the heat absorbed by the object divided by the mass and the change in temperature. Okay?
What did you use? 3.
3, because that's defined. That's our, so it's defining the specific heat. Does that make sense?
Mm-hmm.
Definition sign. All right. This isn't usually how we use the formula. We rearrange it to use it. What are the formulas, or what's the units, though, for specific heat?
Grams. I'm sorry, joules per grams degrees Celsius.
Close. Joules per kilogram.
Oh yeah,
Because this is physics.
that's not what I know.
We use good units. Okay. So these are the units. It's energy per mass degree Celsius, right? Now there are chemistry units which actually don't tell them, but these are useful units for a change. Don't let them know I said that. But in chemistry, you're going to use calories per gram degrees Celsius. Anybody heard of calories before? Right, it's a unit of measure of energy, heat.
4.184 joules.
Yeah. So, yeah. So we'll look at the conversion. I think there's a decimal. I think you're off by power.
That's crazy.
It's kilocalories, I think, is it?
I don't think so.
Because 1 calorie. I don't know. I'll look up the unit. It's 4.186, but I forget where the decimal is. We'll look it up though.
What is the C again?
Specific heat. That's the symbol. Specific heat. Okay.
Whatever I used worked on last night.
You do what?
I don't. Whatever I used worked last
Oh.
night.
Oh, you did homework last night? The way we usually write the formula is Q equals MC delta T. That's how we use it. Right? Okay, according to this formula, heat can be positive or negative. Right? When is heat positive? How do you calculate delta T? MC.
Yeah,
When the final temperature is higher than the initial.
Yeah, so Q is positive when object is warming up because final is higher than initial. Heat is negative when what? The object is cooling off because it's losing. The final temperature is lower than the initial. So heat can be positive or negative. So we're going to get now. Okay, so let's heat these objects, see what happens. So let's turn on the fire. Right, and what's happening to the objects? They're vibrating, right? And notice this one's vibrating more than that one because this one is at a higher temperature. Small specific heat, it's easier to raise the temperature.
Pause. So you
Pause.
know when you're like you see a car and it's like the car is running and like it depends like it's like usually like a hot day or whatever like that and you could see kind of like how that looks like the.
Yeah, the air molecule on the road too. On a hot day on the
Is
road,
that what you're seeing?
you'll see the air molecules. They're vibrating, and what you're actually seeing is the change in index of refraction. Because the index of refraction, which tells you how light bends, depends on the temperature. And so as the temperature changes there, the index it causes the light to bend, and you see that wavy stuff.
That's.
So yeah. So it's the hotter gas expanded. You're not seeing the individual molecules, but you're seeing the effect of that on the light that's coming into that area. It gets bent. So, good question. Another question.
Yeah, is C a constant or no?
It depends. Yeah, it depends on the material. Now, we're trying to treat it a constant. It doesn't have to be a constant. It can change depending on temperature for some materials, but we're going to treat it as a constant. Yes. Oh, it's that. Oh, I mean, we got pretty hot, 120 degrees Celsius. So, but you get the idea, right? That's how this works. Okay. So Q equals MC delta T. All right. Let's talk about. Let's turn this off for a little bit. We'll come back. Let's say I have two objects at different temperatures, and we're dealing with solids still, for simplicity. Object A. Object B, they have specific heats, CA, CB, they have mass, MA, and B, and they have initial temperature, TA, TB. Right, so these two objects, we know these properties, specific heat, mass, temperature of the object. Let's make A, TA greater than TB. But it could be the other way, I just picked one. I'm now gonna put these objects into thermal contact. Right? So I'm going to connect these objects. I'm going to allow heat to flow between the objects. Okay, what's going to happen when I bring them into contact with each other? B is going to heat up, A is going to cool down, right? Heat's going to leave A and go into B. I'm going to call this QH for the hot object and QC for the cold. So heat's leaving A and going into B. Right? Make sense to everybody? What can I say if I were to add QH plus QC? What do I get? Say it out loud for us.
0.
Yes! 0. Why is it 0, somebody? This is something we saw in physics 1.
They're gonna reach like equilibrium.
Well, it's going to reach equilibrium. That's when the heat flow stops. But why does the hot heat plus the cold heat equal 0? Physics 1, that concept. We didn't talk about it. Well, we did, but we're going to talk about it in terms of heat.
Some of these.
Some of the heats are equal to 0. Okay, you just said what I said. Conservation of, what is heat? Energy. It's conservation of energy, right? If I have energy leave one system, that amount of energy has got to be absorbed by the other system. This is conservation of energy in terms of heat. So if you remember your formula, conservation of energy, WNC, right? Plus U naught plus KE naught plus KR naught equals U final plus KE final plus U final. This WNC friction could produce heat. That's usually what friction does. This WNC will go into heat. What was WNC? What was WNC?
Work not conserved.
Conservative. Yes.
What's KR again?
Mm-hmm.
Like,
Rotational energy.
Okay, right.
Right. So we're adding to this. Now we're adding heat into this idea. Does that make sense, everybody?
So,
Yeah.
so heat's gonna be a non-conservative, right?
Heat is where the friction is gonna. This you can think of kind of replacing by Q,
Q.
right? Because the heat, that friction will make heat. Right? Does that make sense, everybody? We'll do a problem on it if we have time today or Wednesday. You know what? You guys take Monday off. You okay with that, Mary? No. My treat. So we'll do it Wednesday. All right. There's a difference between heat and the energy of an object. So let me give you that. So we're going to use the same symbol U, but U, now we're going to use as the internal energy. Right? It's all the energy of all the molecules vibrating. So when you measure the temperature, like we measure the temperature of a gas, we're measuring the average energy, but we're also measuring the total energy contained in the gas, because it's N times the average. Right? So we're going to use U. So we use U for potential here. We're going to use U again, but it's internal energy.
Just for clarification, U is up there twice. U final.
Oh, I just wrote it.
Okay, just this range.
I just got excited. Okay, makes sense, everybody? So what heat is a transfer of energy. U is internal energy, right? So what's happening to object A? It's internal energy. It's decreasing. And the internal energy of B is increasing, right? Does that make sense, everybody? I could say that delta UA is equal to QH, because the energy went out, right? And delta UB is equal to what? QC. It's being absorbed. Right? Make sense? So I want you to get all these ideas together. Yes, quick.
We also should have a QR final, right? K.
Oh, yeah, that's what I missed. See, I wrote the wrong one. It should be KR final. And I wrote, thank you. I wrote U final again. I just wasn't thinking. It's been a long day already. Traffic, one lecture. I gotta go to the lunch for the new students and lab. It's busy.
Oh, yeah.
You don't need to do the lab.
Actually, you know what? You're right. So we'll just do syllabus and let you guys go early today.
Really?
Yeah, my gift.
Are you real?
I'm the best professor ever. You got that on video.
I got that on video.
Right, cheers to joy.
That's right. They're all excited. Let the record show. All right. So QH plus QC equals 0. Let's work with that. See what that means. How do we calculate Q? We just use MC delta T. So this is mass of the hot, specific heat of the hot, delta T of the hot, plus mass of the cold, C of the cold, delta T of the cold, equal to 0. Right? That's what that formula is telling us. And how do I calculate delta T? T final minus T initial, right? So I get MH, CH, T final minus T naught, or TH, because TH is the initial temperature of the hot, plus MCCC, T final minus TC equals 0. So I can solve this problem for the final temperature, right? I can figure out what the thermal equilibrium is. Right? I would just multiply and divide, so let's do it. So we're gonna multiply this through, and then bring things around and get T final. So let's do a little bit of algebra here. Then MH, CH, T final minus MH, CH, TH, plus, same thing with cold, MCCC, T final, minus MCCC, T cold, equal to 0. Right, and I'm just gonna solve for T final. So I'm gonna take TH and T cold terms to the other side. So MH, CH, T final, plus MCCC, T final, equal MH, CH hot, plus MCCC, T cold. Factor out the T final. And then divide, so I can get my final temperature. So there you go, that's kind of the idea, right? But in lab, we're gonna have more than 2 objects, so you would just add another Q, right? If you had 3 objects, maybe you had, maybe you considered the specific heat of the container, because this has got to be inside something, right? So then you would add another C. But it's the same process. Okay, everybody follow?
Yeah, quick question. So T final is gonna be the temperature for both, right?
Yeah, it's the equilibrium. It's thermal equilibrium.
So they're gonna be the same temperature.
Yes, that's the idea. When you bring something hot and something cold, you mix them. What happens?
Same temperature.
They come to equilibrium. They right. So I got ice in here, and I put in T, and what happened? The ice was out of the freezer, so it's colder than 0 degrees Celsius because the freezer is colder. And the ice was in the tea was in the fridge, so it's like 32 or 33. It's just above freezing. The fridge, 35, something like that. And I mixed them. What happens? They come to equilibrium.
How cold is a freezer?
You want to freezer cold. You don't want to write it at 0
Less than
or
32.
at 32,
Yeah.
because what happens? It's got to defrost, and then the freezer rises, and then everything will melt. So you keep your freezer around 0 Fahrenheit.
Really?
I have
Well,
mine
Yeah.
in the fridge
I don't
at
think you can
37.
change mine here at least.
It's probably. I mean, it's just the way they're set. There's,
And
and you keep your fridge pretty close to 0, like
If
35,
my oven
34.
would still work, if my fridge would still work.
Yeah, put a thermometer in your freezer. See what the temperature is. Well, you just buy one on Amazon. Fridge thermometer. Boom, $5.
For sure.
Delivered to your dorm.
My door.
Do they deliver up to the dorm?
No.
That'd be nice. Wouldn't it?
It's a classy PVA fridge.
Wait, do people that live at Tortoise have to come here to get their stuff, or does it get shipped to Tortoise?
I bet it gets shipped to Torrance.
Yeah, you
That must
think.
be-
I mean,
Yeah, I hear that place is great. Like, why can't I live at Torrance? You know what I mean?
Yeah, where's the staff house?
That's what I'm saying.
there's not enough room for us.
I know, right? Okay, so this is the idea. Maybe we should try a problem. What do you say? I mean, you already did some.
I'll give a second.
But it doesn't hurt to try one, right? Nobody's agreeing with me. Come on now. Yeah, I'll email the e-learning, see what's going on. I heard across campus they're having trouble with the same.
That's not shocking.
All right, not just our class, but like math courses, other
It's not
courses.
just like Cengage. I've heard it has like the most problems.
Yeah.
What is chemistry? Like what platform?
Is it a Cengage or is it not
Yeah,
Cengage?
it's some odd.
Well,
different-
like this is through WebAssign, right? Like,
Oh, the same company.
Our
Yeah.
WebAssign
Yeah.
through Canvas, but chemistry is like OWL something, and it's like I swear this thing was designed in like 2010. Like it's.
It's old, yeah.
Nice.
Yeah, in calculus too, we don't use Cengage. We use
I
Wiley.
love.
Oh,
that
we use
though.
Wiley.
Was nice.
That's a great book.
I miss the Wiley days.
Or the Wiley
It was way
interface or the book? Is it a book?
It's a book, I think.
That's what
Yeah.
you would use in Calc 1 too.
It's a good book. I had that. I think I had that book years ago. Is it a new
Calc
edition?
2?
Huh?
Well, it's Calc 1 and 2.
Yeah, we had the same book for Calc
Same-
1, 2, and
same
3.
literacy.
So maybe not.
Is the book determined on the professor, or is it just like?
That's a good question, yeah, who determines what books we read?
It's partly the professor, partly the department. It depends on the course.
Because like you would think, you know, all the calcs would use the same book.
They don't.
But
So it
Well, 1 and
depends.
2 is the same, but Calc 3 is a
Yeah.
different book. I didn't mind though, cause it was the same as physics at that time.
yeah, I know,
Like
right?
physics
It's really
and
nice when they're all
physics.
like the same platform. They all are just like.
Yeah, that's that.
Yeah, but I don't know what kind of mess chemistry is.
Chemistry's a hot mess.
What do you guys have for that?
Who? Professor?
Yeah.
Mercy.
Oh. Is he good? Or she? Yeah.
She's good, yeah, she's good.
Alright. Okay.
She's intense. She's nice.
Reminds me of like an old school teacher.
You can tell she does language, so.
But you probably like, it's probably good enough.
Sorry, I'm looking for a problem.
For something like chemistry. It's a lot of work.
It's probably
Eh, come on, give me a good problem here. That one doesn't have answer. That one's got
I think
answers.
if you show up like to her office hours and you show up to class and you show up.
Okay, let's do number 9. Number 9. Okay, can you guys? Oh, you got hit. You can't even see it. All right, I'm gonna pull up. We're gonna try number 9.
Wait. No. Okay.
You guys get to practice this stuff. Hmm. Okay, are you ready? Okay, number 9. A combination of 0.25 kilograms of water at 20 degrees Celsius and 0.4 kilograms of aluminum at 26 degrees Celsius and 0.1 kilograms of copper at 100 degrees Celsius is mixed in an insulating container and allowed to come to thermal equilibrium. Ignore any energy transfer to or from the container. Find the final temperature of the mixture. So we need some specific heats. So we'll have to look them up. But let's see if we can do this problem. So I showed you an example. I did the equation for 2 objects, but now we have 3, right? So see if you can figure out how to do this. Look, we can cut the class in half. Right here. So I gotta give you guys a name. Oh, you're the iguanas.
Okay.
I mean, it's on your shirt, right? So Team Iguana and Team Blue. You're all wearing blue. So Team Blue, Team Iguana, 1,000 browning points. Let's see if we can do this. You gotta draw a picture, right? So you got 3 objects, you got heat transferring. Right, so we got water, we got aluminum, and we got copper. Which is my cold object? For sure.
Water.
The water, right? So here's my water in the container. And what do I know about water? I know the mass of water, and I know the initial temperature of water. Let's call it TW, right? Make sense? And we need a specific heat of water.
Do we need to convert that?
I would keep it in kilograms, I think.
No,
Celsius to Kelvin.
Oh, no, we can do things in Celsius. Okay, here's how you know if you can do something in Celsius. If your formula starts with a delta T, like thermal expansion, it had delta T. So that's fine. Specific heat has delta T. So if you start with a delta T in your general formula, you can do Celsius. Ideal gas law, PV equals nRT, you gotta do Kelvin, because it's not delta, it's TT. You see the difference?
Mm-hmm.
Because here, when you do a delta T, you're gonna subtract, and so the 273 will subtract out, so it doesn't matter Celsius or Kelvin. You can do it either way. Because one's positive 273, negative 273. So we'll just do Celsius. Okay, specific heat of water. Where did I put my phone?
Oh, here.
Oh, I can't look up the specific heat of water. Alright. Alright, write it down, I'll see if I can find a table. Oh, here. Let's see, water. These are in the wrong units. Here we go. That's not enough.
Use ChatGPT.
Huh?
ChatGPT.
Oh, ChatGPT.
You're really good at that.
Alright, Google will do it too, right?
Yeah.
Specific heat of water.
There you go.
What is it? Aluminum?
Yeah, aluminum and copper.
Aluminum?
Oh, the co-pilot.
Okay, there you go.
There you.
Those are in grams. I want them in
So-
kilograms.
Just ask for the units you want. And
And joules per kilogram times Celsius. Capital. There we go.
there we go.
4182, 897, 385. What is 4186? Okay. You guys wrote those down so we can go back to the problem?
No, get her them all, right?
You need all three.
Yeah.
Because they're aluminum and copper. $897,385. That's not our problem, right? But that is our problem. No, that's the other class. Okay. Here's our problem. 400 grams of aluminum and, or 0.4 kilograms of aluminum, 0.1 kilograms of copper. So there's water, here's aluminum, here's copper. Mass of aluminum is 0.4 kilograms. Temperature of aluminum is what? 26? What's the specific heat of aluminum, anybody?
385.
385? Joules per kilogram Celsius. And then copper, mass of copper is 0.1. Temperature of copper is 100. Specific heat of copper, 897 joules per kilogram Celsius. The water was 0.25. And the temperature of water is 20 degrees Celsius. Right? Okay. So what's our overall formula? What formula are we gonna need? I have one on the board for you.
This one.
We're gonna need that one. Q equals MC delta T. But we gotta do what? We gotta add all the heats together.
So we can use the one that you derived, right? The T
That's-
final.
That's for two objects.
We can just add another one, right?
Yeah, but not at the end. You I mean, you kind of gotta. I would go to the beginning.
You have to have like the three of them and it equals 0, right?
Yeah, I would do it just to be careful. 'Cause I'm not sure you can just miss. Yeah, I would do it that way, just to be safe. So let's pull up a white screen. Why don't we do that? Question? It might come out until you just add it
Yeah.
in T final, but it doesn't hurt to do the algebra. I mean, who doesn't love algebra?
So, right.
Right? Matthew gets it. So I have Q of water plus Q of copper plus Q of aluminum equals what? Equals 0, right? You with me, iguanas?
Yes.
All right, blues? All right, now see if you can take it from here. See if you can work it from here. It might be you just add. It might.
Yeah, take a look.
Yeah, you might be right. Did you work it already?
Almost. So what I did, just add this.
And then that might work out just fine.
It does have to run.
Okay, all right. That was convenient. But you know me, I always like to go back to the beginning.
all the way.
Nothing like starting at the beginning. So what do you guys get for an answer?
Yeah.
I don't have my calculator.
Oh, you don't have your calculator?
I'm using my phone.
So this would be mass of water, specific heat of water, T final minus 2. I bet it does. Now that I'm writing out the algebra, I think you're right. MCCC, T final minus TC plus mass aluminum, specific heat of aluminum, T final minus T aluminum. Yeah, now that I'm writing it out, it looks like it's gonna work out. Because all those are gonna go on that side.
Yeah,
You're gonna factor out a T final is gonna be the same.
there you
Okay, that turned out easier than I thought then.
go.
I just never allowed to assume something to begin with.
Yeah.
But it works out. So we have MW, CW, TW plus MCCC, TC plus MAL, CAL, TAL divided by
The mass and specific heat of all of them.
right? Like that. You know what this looks like to me?
Hmm?
It's like a weighted average. Doesn't it? Kind of weird.
If you say so.
Like if you were to calculate the center mass of an object, you take the mass of the object times its location, add them all up, and divide by the total mass.
Mm-hmm.
But here I'm taking the mass times the specific heat times the temperature of each one and divide by that quantity. So kind of looks like a weighted average.
The weighted average of the temperature, right?
Yeah.
Yeah.
So with the mass and the specific heat.
As a constant. Mass and specific heat as a
Yeah,
constant.
as a constant, yeah. That's what it looks like. All right, what do we get for T final? Should we just pull out the answer? You guys can put it in numbers, right? I don't need to put it in numbers for this. Do I? 23.6. So what does that mean? If I got T final,
4,182.
Thank you.
T final as 23.6, what happens?
The copper is a lot colder than, because the aluminum and the water.
Yeah, the aluminum actually warmed up, right? Didn't it? Or no? No, it cooled. It cooled a little bit, right? 26. The water warmed. And the copper cooled a little bit, but the aluminum warmed a little bit, but the copper cooled way down. Okay.
Would you say it's easier to lose heat than it is to gain heat?
It's the same.
Really?
Yeah, I mean,
Like
Yeah.
it's easier for something to cool off than it is for something to.
I mean, it's relative because you're talking about because when you lose heat and gain, you got to be losing it to the environment or gaining from it. So it depends on your environment. You know what I mean?
Mhm.
So like around here, it's harder to cool off because it's always hot outside.
Mhm.
But it's easy to take something cold and warm it up because the environment's warm. Because you gotta speak to it in terms of the whatever it's thermally connected to. Does that make sense?
Yeah.
So
Why is the specific heat of water so high?
it's the problem. Water.
What does it mean though? Does it mean that it's hard to boil?
It takes a lot of energy to heat water. So it's like you put a pan of water on the stove and you're gonna boil it. It
Yeah.
takes a long time to boil because water has a large specific heat.
But there's also large quantities.
And there's a large quantity. So that's why, yeah, a large quantity and a high number. Like when I lived in Chicago,
Mhm.
you know, around the lake, it takes a long time around the lake to cool off because the water, even though the air temperature drops, like it gets winter, the lake's a huge reservoir of water, so it takes a long time to raise and to change the temperature of water.
Mhm.
You got to take a lot of heat in and out.
Why are the oceans always colder when they're outside? Are they not?
Yeah, they are, but again, right, you have a weak connection because you have to have the air molecules hit the water, transfer the energy, and the water has such a huge specific heat, it's hard to change. Same thing when the temperature cools and the water is warmer than the outside, it's hard to change the temperature of water because there's a large specific heat. So you gotta either put a lot of energy in or take a lot of energy out.
Also, like, the lack of light. Just 'cause the farther down you get.
Oh yeah, and then you
And there's more
right.
water lower down. So.
Yeah, it doesn't absorb. The radiation gets reflected, and only absorbed in the top. I mean, there's a whole. Water's a really weird substance. Like it's one of the only substances that expands when it freezes. Most objects contract when they freeze. They go from liquid to solid. Water. It's one of the like. There's two substances: water and something else. I forget what it is. So water is really weird. Even though it's all around us and it's common, it's a weird substance. All right, this was fun. I hope you guys had a good time. All right.
No.
I got a different number.
You got a different number.
Pretty close. Like
Okay.
26.28.
Maybe they use. See, I thought we used 4186 instead of 4182. So
You'll give us those, right?
yeah, I do.
Yeah.
I think that's what the book uses.
No, basically, it's that.
You have to memorize every specific thing of every material known to man.
No.
All right, I'll see you guys. Have a good one. Yeah, turn that off.
Bye.